Okay, so I'm working with a group, a pretty diverse group, including a philosopher, a mathematician, and a psychologist. And that's kind of the theme. The first half of my talk is going to be something I think is probably preaching to the choir here, which is, I mostly try to use this kind of talk to motivate undergraduates to try to study outside their field. And this is a quotation from Robert Heinlein, Specializations for Insight. So if you really want to understand what you're doing, you should probably look at what other people are doing and saying. I gave a version of this talk at A-Life in New York City on Wednesday, and somebody who's familiar with entomology said, well, there's all this new data that many species of insects are generalists. I said, well, of course, because when you study real life, there are no generalizations. But at least I could take this as kind of a departure point. An image I like to use is that, especially students, say, moving away from math and towards the liberal arts and humanities, think that they want to do something that they'll really enjoy and it doesn't have any math in it. And of course, when you look at what's underneath, right, very often that distinction is illusory. And there's a single system, and you're just sort of looking at it at a superficial level, not really seeing the commonalities. And what I'd like to argue is that it was the philosopher Ludwig Wittgenstein in the early mid-20th century who was probably the only one who had the general background in both engineering and in philosophy, and to some extent in psychology, to understand the kinds of problems that I think really, he was very prescient about the kind of problems that would plague AI cognitive science, and especially linguistics, the field that I come from, I was trained in for much of the latter half of the 20th century. And I think with disciplines like AGI or movements like AGI, we're only starting to recover from that kind of thing. So what specifically am I arguing against? Well, I think probably again this audience doesn't need a lot of convincing that the idea of the mind as a Turing machine, sequential von Neumann symbol processing machine is kind of fundamentally broken. So of course what we end up doing is we want to answer a query based on a kind of subject predicate object sentences. We have to chase pointers, right? So let's say that instead of asking, what's this about? It's about love. What if I want to know who loves who? Okay, who are we talking about? So I have to chase the pointers down, right, back and forth, and eventually get to, that Mary is the subject of the sentence. I'm going to chase the pointers back up, and of course, in addition to sort of suffering from an implausible slowness, sequential access, you also have brittleness, right? So if I take away just one, you can just sort of flip or lesion if you like one bit, the whole thing just falls apart, right? So kind of this is almost a straw man now, this kind of representation. If you want to really talk about, if you really are concerned with the kinds of things, I think, for example, Richard Granger was talking about, like actually understanding the mind in terms of the brain is the only positive exemplar that we have. There really is no other game in town. If you start off with representations that are fundamentally un-brain-like, even at, forget about dealing with the actual physiology of the brain, it's just that it's very, very implausible as having any kind of neural or biological instantiability. I think you're off on the wrong foot. Another kind of mistake I think that certainly linguistics and cognitive science and traditionally AI made was pointed out by Wittgenstein in the beginning of the Philosophical Investigations, the second major work, which is considered the later Wittgenstein, where he sort of departed from this positivist view that he started with in the 20s and moved more towards his own kind of, what was then very, very strange view about thinking in language. And he said, it's a fundamental mistake to think that if you and I are involved in building a building, and maybe I'm a terrible French speaker, maybe your English isn't so good, but we agree that I'm the foreman, and when I say slab, your response should be, your behavior should be to bring me a slab, and then we could, if I say hammer, you bring me a hammer. And Wittgenstein, anticipated, I think, a lot of this kind of deep structure nonsense from linguistics, which is that underlyingly there has to be a kind of proposition or a command, bring me a slab, and that the utterance slab represents some kind of elided, degraded form of that. So he said that's fundamentally wrong. He said if the utterance slab functions in our language game to affect that action, then I've successfully communicated with you, and famously said there's nothing else, there's nothing below the surface, right? Everything is visible. More controversial, I got into a lot of trouble with A-Life for quoting Wittgenstein on this. Another thing Wittgenstein said was, don't mistake communication for it being in the world. Meaning that, if you think maybe if a lion could speak, we could talk about his environment and some kind of, and he said no, because the lion's world, based on what he does, to earn his living, if you like, chasing gazelles and other things, is so different from ours that even if he could communicate in a kind of sequential serial language like you and I use, if there were Lionese that had sophisticated grammar like English or Swahili, we still wouldn't be able to ever understand it because our fundamental world in which we're embedded is so different from his. And what I want to focus on then, the quotation, rather lengthy quotation on which I based the subtitle of the talk, is, again, something I think probably in this group isn't all that controversial, but Wittgenstein was saying, you know, another kind of mistake that you can make when you're thinking about how to represent the world is to think that, you know, if Ben is thinking of a cup of coffee and I'm thinking of a cup of coffee, that there will be some mechanism. And again, Wittgenstein said this well before, you know, even things like EEG, let alone MRI, fMRI, but that the search for some kind of underlying invariant in my brain and Ben's brain is just hopeless, right? It's just hopeless. It's a mistake to think that because we appear to have a commonality of representation, that entails a commonality in something that can eventually be physically observable. Okay, so what kind of, you know, to actually get to some results and some actual math and stuff, get away from the philosophy, what kind of representational scheme would you come up with if you took these critiques seriously, these problems seriously? And I'm using the term architectures here, plural, because I do not have a cognitive architecture, cog or SOAR or anything remotely that complicated. But I'd rather like to talk about architecture in the sense of, technical sense that computer scientists use. What's the instruction set? How many bits do I use in my, is it a 32-bit, 64-bit machine? Is it Intel? Is it ARM? Is it MIPS? Okay, so that sense of architecture. So to start off with, when you think about a very different notion of what a symbol is. Okay, I'm kind of starting off at the basic level. Most of this audience knows what a vector is. Right? Of course, we can think about a vector as a single number, right? I don't know, negative 1.5 or positive 2, right? We can think of it as an arrow, right? If we have I'll talk about what sometimes goes forth we call bipolar representations. If you have positive negative 1, right, in our vector space and it's one-dimensional, then we can have 2 values, right? If we have 2 dimensions, we can have 4 values. Okay, I'm assuming that for reasons I'll mention in a moment that the vectors are orthogonal to each other. Okay, and of course this scales up. If we have 3 dimensions, we have 8 vectors. And more generally, as you probably, I'm sure most of you know, n dimensions gives the rapidly explosive 2 to the n vectors. Okay, now this seems like recursive dimensionality, but it's actually something I'm going to talk about as a property that we can exploit. So what's interesting too is that although technically most of the vectors will not be strictly orthogonal to each other, as they were in those low-dimensional examples, there are very many nearly orthogonal vectors. What do we mean by that? Well, if you have a very high-dimensional space, like a 10,000-dimensional vector, where each element is just positive or negative 1 or 0 or 1, you can degrade any given vector pretty significantly, right? You can basically, you know, lobotomize the thing and still get back to, if you have some kind of recovery mechanism like a Hopfield net or a maybe you'd be more neurally plausible mechanism. Terry Stewart has published on that recently. I mean, you can actually get back a pristine reconstruction of the original vector. So these vectors are highly, highly robust to noise. Okay, so they have a high representational capacity and highly robust to noise. Sounds like something that we kind of associate with brains. Okay, so what are some additional properties? The reason we use positive and negative 1, there are other schemes like a convolution. Mathematically, this is extremely simple. This is a single infix operator in MATLAB, the dot star operator, right? These vectors are self-canceling. So if I have A associated with B, so you can think of an associative memory. If I want to recover the association, who's associated with A, right? I multiply them together element-wise. A times B gives me back B. Okay, so you can build up something like relational database, right? If this property is associated, if this slot is associated with this filler, then I can multiply by the filler and get back the slot. I can multiply by the slot and get back the filler, right? And it doesn't involve any kind of variables or anything like that. It has the usual properties, as you probably know. Element-wise vector operations are associative and commutative. Multiplication distributes over addition. So I can build up, in fact, sets of associations. So if I have some set of associations, B is associated with A, and C is associated with A, I can recover B and C. I haven't shown this because the transcription of it gets too big to put on paper. That can be in the presence of many other associations. Okay, so maybe I should put dot A times B plus C times A. And I think most importantly from the perspective of practical implementation and neurobiological plausibility, you get constant time recovery. Okay? So if I have a query, if I have some properties associated with some individuals and not others, right, I can query. And the important thing to note is that each of those lines that I've just stepped through is our sort of conceptualization of what's going on. This is a constant time operation. Everything's a single vector, a single knowledge base, and I can probe it with various queries. And that probing and recovery takes place at constant time. It's just vector element-wise multiplication. So if I had some massive scalar architecture, right, then I could do that in whatever the constant time operation of that architecture was. 5 minutes, good. I'm almost done getting there. Thanks. Okay, good. So as I mentioned before, right, you do get some kind of distortion in the vector space. We call this noise, convenient term. You can clean it up using the Hopfield net, or there's a spiking neural net implementation of that. But so the point is, again, you don't have, it's a form of lossy compression, if you like, but they're very plausible and easy to implement mechanisms for undoing the noise. And if you're only interested in a sort of like maximum likelihood kind of question, the noise is fine, because then you basically just have a set of patterns against which you compare your result using a dot product, and you can pick the maximum, as I'll show. Okay, so some applications. The famous vector cube. Wittgenstein's famous example of the duck rabbit, his idea being, I can't see it when somebody says, say I'm seeing a duck, I'm seeing a rabbit, they don't see it. I'm not seeing an image as a duck rabbit. More conventionally, people are familiar with the Necker cube. The PDP implementation of this, I'm sorry, the only figure I could find on the web was tiny, but basically Rumelhart and McClellan and their colleagues did a localist representation of this, right, where each node corresponded to a proposition. So, vertex P is in front versus vertex P is in back, and that will reinforce or inhibit other propositions based on the consistency. So what we were interested in doing was seeing, this is kind of the final, to me, the last stand of localism, the idea that there are certain problems that are inherently, fundamentally better handled by sort of grandmother cell type representations. So my colleague Ross Gayler and I sort of have shown that this kind of, you can think about this as kind of the reinforcement mechanism as being a kind of set-wise intersection using vectors. So if I have a vector representation of P in front and T in back, and T in back and U in back, right? Multiplying them together requires something more than straightforward vector operations, because they'll just cancel each other out and you get noise. Okay, so how do you get these two T in front, two and T in back hypotheses to reinforce each other? And Ross Gayler came up with a very clever neural intersection circuit. I mean, I don't have the details for this, but it involves one additional operation, permutation. Okay, again, permutation is another very neurally plausible mechanism. If you just think about, sort of synaptic connections are essentially random, as someone said this morning. That's a permutation. Okay, I'm getting there. So we had applications in terms of sort of conceptual things. We also did a paper using this for graph isomorphisms. Okay, you get another area where the localist representations are sort of the only ones that people are working on. We showed how it can be done using this neural circuit with our distributed vector representations. And then maybe most apropos, this conference, although very modest kind of accomplishment, is what I did a couple of years ago. I had an undergraduate student doing an honors thesis on localization and mapping, so he and I played with the VREP robotics simulator, and we have some code that essentially takes, in the upper left, you have just a simple Python or C++ pseudocode for a hierarchical behavior-based robot that can exit the corral reliably, based on a kind of Rod Brooks 1990s style subsumption architecture. And I basically sort of built a vector symbolic representation of that, where you have a sensors going into your sort of knowledge base. Again, the knowledge base is just some 3,000 dimensional vector, which then projects outward to the actuators, the left and right motors. And I just used hard coding, because we currently don't have a learning mechanism for this stuff, to actually get the right behavior. And so to finish up, we also have like 1 minute. Okay, so I'll give you a URL for this stuff. Okay. So in 1 minute, we also have a nice demonstration of solving an IQ task like this. The idea being sort of taking seriously Wittgenstein's ideas that symbolic variable-based rules like induction, just really hard to justify from a philosophical standpoint, or certainly biological standpoint. So we just kind of implemented that. And since somebody before asked about URLs, so there's the URLs for the Wittgenstein VSA exemplars I talked about, and if you want to run the robot demo, it's at the second location. Thanks.